Heat, specific heat capacity. So in 2006 higher level question 12c, we had a calculation centering around power and specific heat capacity. So as always, we're going to break our question down into how many different questions there are within it. So this is part C. So not to cause confusion, I am still going to call the first part of the question A. Then the next thing we're doing is the calculation, which is B. And then in C, explaining why. So we have 3 parts within this question, okay? So the first part of the question, part 1, is our definition. So we have to define power. So power is basically our work done per unit time. So it's the rate at which work is done. So power is equal to work over time. Or you might want to say power is the rate at which work is done. And of course, if you're saying P is equal to W over time, P is equal to W over T, you must say P is equal to power, W is equal to work, and T is equal to time. So if ever you're using a formula for a definition, please be careful to always make sure that you're stating the notation. So any 3 of those is acceptable. Okay, so there was 3 marks for your definition. The second definition we need to give here then is specific heat capacity. So how do we define specific heat capacity? Well, we say specific heat capacity is the energy needed to change the temperature of 1 kilogram of a substance. So specific is always specific to its mass. By 1 Kelvin. Okay, now if you do say by 1 degree Celsius, that's fine, because the change in 1 Kelvin is the same as the change in 1 degree Celsius. So again, the energy needed to change the temperature, you'd get 3 marks, and then of 1 kilogram by 1 Kelvin, you'd get 3 marks. Okay, so we'd have 3 and 3. Okay, so the next part of our question is our calculation. So we have to first of all calculate the energy required to raise the temperature of the water to 100 degrees. Okay, so we're bringing it from 15 to 100. So it's only reaching 100, it's not at 100 or going beyond 100, so therefore we're not going to have any change in state. So it's just a change in temperature. So for our change in temperature, we need our mass, but we can see the mass is in grams, change of temperature, and down here in the bottom in brackets, we also have specific heat capacity. Okay, so for the first part of the question, we're looking for the energy, which is Q, and that's going to be equal to mc delta theta, which is page 58 in our maths tables. And we have the mass, we said there is 400 grams. So divide that by 1,000 and we get 0.4 kilograms. Our specific heat capacity is water, and they've given it to 2 significant figures here. Okay, so again, don't be under the assumption that you need to know that value off by heart of 4,180. So it's joules per kilogram per Kelvin. And then our change in temperature, so delta theta. So it's going from 15 to 100. And that's equal to 85 degrees Celsius. Okay, so therefore our heat energy is our M, which is 0.4. Specific heat capacity is 4,200. Change in temperature, 85. And of course you can use E here for energy either. We just have a tendency from our textbook that we're using to use Q for our heat energy. But of course in your maths tables you'll see delta E for the energy needed to change the temperature by 1 Kelvin. of 1 kilogram of a substance. So if we're multiplying out our brackets here and we simplify, well, what do we get? We get 1.428 by 10 to the power of 5, and that is joules. So again, we have 3 for our equation, and then 3 for substitution and getting out the correct answer. And of course, if you've no units or the wrong units in there, you'll lose a mark. So again, any of these calculations, remember your units, okay? And if you can't remember your units, what page do you go to? So of course, page 66 in your maths tables, you'll see energy there is in joules. Okay, so the second part of the question, let's go back to it. What do we want? Well, we want the energy supplied by the kettle per second. Now, if we look, we're told the power rating is 3 kilowatts. Okay, and you have to remember that power, we defined it here as rate at which work is done. In other words, work over time. In other words, energy over time. So the power rating of our kettle is 3 kilowatts. Okay, and what's 3 kilowatts? Well, that's 3,000 watts. And what is that? Well, that's basically 3,000 joules per second. So therefore, the energy supplied by the kettle per second is equal to 3,000 joules, or in other words, 3,000 joules per second. Okay, and again, you might want to say here, power is equal to energy over time, which is where we're getting our joules per second from. Okay, and we were getting 3 marks then for that. And then part 3, well, what do we want? This time we want the least amount of time to heat the water to 100 degrees Celsius. So the time taken to heat the water, well, what have we just written down? Power is equal to energy over time. So therefore, if we want time, well, let's rearrange that equation. So multiply both sides across by t, gives me pt equals E, and divide both sides across by p. So in other words, we get energy over the power. And what's our energy? Our energy is 1.428 by 10 to the power of 5. And what's our power? Well, our power was 3,000 watts. So again, you have to make sure you're working in watts and not kilowatts. So again, that is 47.6 seconds. So again, 3 for subbing into our formula and 3 for our answer. So we had 15 marks in total for our calculation. So the last question then says, well, in reality, the time taken to heat the water will be greater. And why is this? Okay, so why would it actually take longer than 47.6 seconds? Well, in an ideal world, obviously all that energy would be transferred directly to the water, but that's not the case. In reality, we'd have heat lost to the surroundings. Meaning it's going to take longer to heat up the water and therefore bring it to 100 degrees. Okay, or you might have some heat lost to the kettle itself. The kettle might actually absorb it, or you might have a bit of evaporation because the water is beginning to internally boil, and some of that water, then some of those molecules are going to escape. So a nice little question there. So total for that obviously is 28 marks. Because it's only part of question 12. So I just put up here, this is 28 marks. So obviously in question 12 you always have to answer 2 parts to the question to get your full 56 marks.